name is Alejandra Perez.
I'm Joey.
I'm Sonia Tomas.
I'm Luis Moreno.
Our mentor is Ashley Larson, and our project is on the effects of citrus greening disease, Florida's challenge, and California's threat.
So many of you enjoy drinking orange juice, but many of you also take for granted the availability of it. Well, Florida farmers, they definitely don't. Ever since citrus greening disease has come and destroyed their orange trees and other citrus-related crops. In fact, there's been a 33% decrease in orange juice production over the last 13 years. And unfortunately, citrus greening disease has been spotted in California, and the further spread of this disease throughout California has the potential to cause serious economical problems that come as a result of loss of crops and the increased use of insecticide. The increased use of insecticide has its problems too with human health, water quality, and biodiversity.
Citrus greening disease works just how a mosquito transmits malaria. In this case, we have the Asian citrus psyllid, which is the insect that is transmitting a bacteria that is causing the citrus greening disease. Some of the symptoms of this disease is the twisting and curling of the leaf, the display of yellow patches as seen here, and the unripening of fruit.
In 1998, we have the first sighting of Asian citrus psyllid in the U.S. This occurred in Florida. By 2005, we have the insect and the citrus greening disease present in Florida. And in 2008, the insect was found in the San Diego region, making it the first sighting of the insect in California. And by 2012, we have both the insect and the disease present in this state.
So, the main goal of the research project is to analyze Florida's data of how the disease has impacted its economic and agricultural statistics, mainly focusing on insecticide use, chemical expenses, and the citrus production, and using those results to simulate what could California go through if this disease spreads throughout the whole state.
Okay, so we use data from the 1997, 2002, and 2007 USDA Census of Agriculture to statistically analyze these three categories: the amount of citrus harvested, the amount of insecticide used per total amount of harvested acres, and the amount of chemical expenditures.
One of the methods we will be using is a t-test, and what a t-test does is that it tests the difference mean. It also answers the question of whether or not the difference is significant or if the difference is not significant.
Difference is another statistical tool we use to measure the effect of the citrus greening disease in the time period of 1997 to 2007 in Florida. The basic idea of difference is to isolate the effect of the treatment by using a control group to remove any time trends that are similar to the control group and to the treatment group.
So our first result for the t-test shows that in 1997, 28,239 citrus acres were harvested in Florida, having a standard error of 6,618.1. In 2007, we see that 16,175 citrus acres were produced in Florida as well, having a standard error of 4,691.87. As you can see, there was a 43% decrease on the amount of citrus acres being harvested in Florida. And for this, we use a p-value. What a p-value does is that it shows how significant the differences are. If the p-value is less than 0.05, then the difference is significant. Anything greater than 0.05, the difference is not significant. Our p-value was 0.067. It was greater than 0.05, but it is. So we say that for this particular data, the difference was not significant. In our second t-test result, we see that in 1997, 53.8% of total harvested acres were spraying insecticide. We have a standard error of plus or minus 3.04. In 2007, we see that 66.9% of the total harvested acres were also spraying insecticide in Florida, and we have a standard error of plus or minus 5.34. We see also that there is a 12% increase in the amount of insecticide being used in Florida, and the p-value here is 0.0173, which is less than 0.05, which shows that for this result, the difference was significant. In our third t-test result, we see that for every citrus acre harvested, about $151 were being spent on chemicals. In 2007, we see that for every harvested acre, about $156 were being spent on chemicals. You see here that there was a 3.1% increase on the amount of chemicals being used for the harvested acres, and our p-value here is 0.5802, which is greater than 0.05. So for this data, this difference was not significant.
Okay, so the main reason of using the difference in difference method is to see if California makes a good control group for Florida. So what we want is our control group, California, indicated in black, and our treated group, Florida, indicated in red, to follow a parallel pattern to decrease and increase in a parallel rate, so that up to the year 1997, where Florida first encountered the insect. So looking at this relationship, the total amount of citrus produced per acre, we can see that both Florida and California do decrease and increase, but they don't decrease and increase at a rate which a very similar rate, which is exactly what we want. So we can, in this relationship, we can say that California, it's not a good control group. So, but then we tested another relationship this time, the percentage of citrus harvested per acre. And again, we failed to see that California makes a good control group in this relationship, as they don't follow that parallel trend when decreasing and increasing. However, when we look at the other relationship of insecticide use per total acre percentage, we can see that they do follow that parallel pattern as simulate, they do follow that parallel pattern that are similar to each other up to the year 1997, which is exactly the one. So how do we calculate the difference in difference value? First of all, we draw a line simulating what Florida would have looked like if it had not been infected by the insect, indicated by the blue line. So then after doing some calculations, we find that our DID value is 0.09 with a standard error of 0.06 plus or minus 0.06 and our p-value of 0.16. As noted before, we use our p-value as a margin to see if this difference, these 2 points, is significant or non-significant. So if our p-value is less than 0.05, it means that this difference is significant. If it's greater than 0.05, it means that it's not significant. In our case, we can see that it's 0.16, so this difference is not significant. So then we went on to 5 years later, in the year 2007, when Florida had both the insect and the disease in the state. As we can see here, California had a large increase in insecticide use, possibly because of the fear of having the insect inside the state and spreading, and because of what California did at this point, we can no longer use California as a control group. So we now must rely on the t-test for accurate data.
So in the project, we looked at three factors that we thought ACP, the Asian citrus center, and the CGD, the citrus green disease, would have affected Florida in terms of citrus production, insecticide use, and chemical expenses. We also used the t-test and the difference in difference to measure the significance of our data. And although our data does not show with absolute certainty that the Asian citrus and the citrus green disease did have an effect on Florida citrus production, chemical expenses, and insecticide use, we do see that there is a substantial difference, and further research must be conducted.
Now that we have a better understanding of what Florida went through as a result of citrus greening disease, we can use that information to help manage the further spread of the disease and insecticide use in California. Now, Florida, their citrus production decreased by 43%, but they were able to maintain a steady level of income in the same time frame. And their insecticide use increased by 13%, but they were able to maintain a steady level of chemical expenditure in the same time frame. So they adapted somehow, and California needs to adapt too, because this disease is non-curable. So we have to adapt, and one way we can adapt is focus on a different crop instead of citrus, and hopefully this will stabilize the agricultural economy. Now, the number one insecticide used to prevent ACP is carbaryl, and carbaryl can be very dangerous on the environment. So we're hoping that our data and research this week can assist somebody in finding an alternative for ACP prevention and hopefully a cure for citrus greening disease.
One component that could improve our research would be to use data that focused on the amount of carbaryl used instead of data that focused on the amount of all insecticides used in citrus acres. Another improvement would be to have an increased number of observations, so that way we could get a better depiction on the amount of insecticide use, citrus acres grown, and chemical expenditures. Using data from other states would have also been an improvement, considering that in our research, California proved to be a poor control group. And having annual data from the U.S. Department of Agriculture, instead of having data that is collected every single 5 years, would have also been an improvement. To end, we would like to thank the Jack Kent Cooke Foundation, our mentor Ashley Larson, the directors and advisors of the Cooke Bridges program, our faculty, and to all others that took part in this program. Thank you.